All right, the null hypothesis is the single most important concept when it comes to understanding p-values. The p-value statistic tells us if we've probabilistically disproven the null hypothesis. That's a lot. It's foreshadowing. It will make sense soon. Let's start with a warm-up today. Let's get your creative juices flow in. I want you to develop a method where you try to prove that all sheep are white. What would you do? And I am not changing the question. Prove to me that all sheep are white. Go ahead, think about it. Take a few seconds. What'd you come up with? I have two answers to this question. Number one, you just can't. You can't prove that all sheep are white. You're probably like, how would I do that? I would need to be all over the country at the same time there for every sheep birth and every... I just can't do that. Or you can get real creative with it and have some fun. So you need to create an elixir that stops your telomeres from aging. Take it, live forever. That's step one. You're going to be living forever. Study physics, make a time machine. Step two. I mean, it exists according to that Dark movie. I mean, I can make it happen. Step number three. Take my time machine. Go back to the first birth of the evolved sheep. If I can start there, if I can find that, I just got to trace back every sheep, to the first sheep. If I can find that for a sheep, I can follow it forward every single time, using my time machine to go back past the migratory patterns of the sheep, but I'll eventually be able to go to every single sheep. Follow all sheep at birth and keep note of their color. Now, I'm only going to do it at birth because I'm not doing this for their entire life. I'm sorry, I'm not doing birth and death. No, I am not. So we're just going to live with that. You can critique it and have my all sheep are white study retracted. I do not care. That's a flaw I'm not going to fix because I am not doing this again. I want to use my immortality and my time machine to do some really good things. Then I'm going to measure all the births, see if they're white. I'm going to continue this and continue this until they go extinct. And, I'll let you know with my time machine if they actually go extinct. But the way we're going, I think they're going to go extinct. That's all I got to say on that one. It's kind of a natural process. Things come, they go. Eventually I'll be able to see if all sheep are white. If all sheep are white, I'd have a record for every single sheep. I'll have the complete sheep genealogy made up. Heck, I might even record their DNA just so you believe me. And then I will have fun with my time machine and my anti-aging elixir after this takes me probably 1 billion years to accomplish. So really, you can't prove all sheep are white. Disproof equals science, though. Can you disprove that all sheep are white? These purple and blue sheep disprove that sheep are white. All sheep are white, right? That's how easy as it is to disprove something, and that's how hard it is to prove something. The thing you need to understand is that disproof is science. This is really the idea of Karl Popper. Karl Popper made this idea popular when he's trying to show, and I'm not kidding here, why Freudian theories were completely unscientific. So those of you that are like me and aren't a fan of Freud, now we can also say not scientific. Science, as we just learned with that thought experiment, does not have the power to prove things. There's no observation of proof. Think back to the sheep. I can't just find 1 or 10 observations. What, if I found 100 sheep that were white, would I be able to say that sheep were white? All sheep are white? No, I'd have to measure all sheep. There are clear observations of disproof. Think back to the sheep example. Science can only work through disproof. You can't prove anything in science. Nothing, nada, never. Stop saying proof. I think it's important to know that the shared scientific hatred of Freud helped to create modern science. But seriously, Freud was just a sexist and racist philosophy major that argued really well. Every time somebody came up to him and I think this proves your theory, he would say, well, what about this observation? He would say, and then he'd say something racist or sexist and work in your observation into his theory by talking in circles and constantly saying, I'm a real doctor, I have a medical degree, that means you can't question me. It's pretty sad, but Freudian's ideas were very popular and scientifically wrong. Now, here's the thing. Freud couldn't lose, right? He takes any observation and massages it into his theory. There's no single observation that could ever disprove the idea. There is nothing. There is no measurement. There is no observation. There is no anything that would disprove Freud's theory. It described all human behavior. And thus it's not scientific. Now here's the thing, that seems great on the surface. You're like, I want to describe the theory that describes all human behavior. No, you want to describe a theory that has limits on human behavior, that makes predictions, specific predictions that can disprove your theory. You're not trying to prove your theory correct. You're trying to disprove it. And if you fail and fail and fail and fail and fail, one day you quit trying because it's not worth your time. You're like, look, I've run 100 studies on this. I'm pretty sure this is true. If somebody else wants to take it on, that's fine. But I tried to disprove this thing and I didn't. That's good science. Trying to disprove your own theories and ideas. So in science, we're trying to disprove the null hypothesis. That's what we are doing when we run a p-value calculation. We're trying to disprove the null hypothesis. Now, what is the null hypothesis? The null hypothesis for a basic experiment is that the two population means are perfectly identical, that the population mean of the control group equals the population mean of the experimental group. We can present this as mu of 1 equals mu of 2, or mu of control equals mu of the experimental group. We can think of it this way. In the control group, it's all humans treated the same way as the control treatment equals all humans being treated the same way as in the experimental group, and essentially it's the means of whatever we're measuring. This is a population. It's not all people in the world, but it's all the people in the world I could fit on this slide, okay? This is the population that we are often interested in. I talked about that last time. And from that population, we can sample a random group of people. A small subgroup of these people. From the population, we sample a small subgroup of people. This is what we do. We randomly sample a small group of people from a population. We randomly sample a small group of people. This is a population. This is a random sample, maybe, maybe not. Regis students on the softball team. Maybe not a random sample, but it's still a sample for the population, right? We have all people, the population of interest. We're trying to make inferences about this, trying to make conclusions about this, and we take samples. Is this a random sample? Maybe, maybe not. I'm not going to go there today. We got a population, a sample of people. You can see I'm just having fun with this right now. The null hypothesis is the thing we're trying to disprove. We're trying to disprove that two population means, not two sample means, are perfectly identical. This is very, very, very important. Mu of the control minus mu of the experimental group equals 0. The mean of the control group, population mean of the control group, minus the population mean of the experimental group equals 0. Another way to state this is that the population mean difference equals 0. And if we had the ability to measure population means, if our control group population mean was 5.01 and our experimental group population mean was 5.02, we would have disproven the null hypothesis. But here's the special note here. Remember, this is a power for omniscient beings. This is a power that we don't have access to. We never sample population data, but if we did, those two numbers, as small as they are, would disprove the null hypothesis. Really, it's a pretty weak hypothesis. If we collected population values that were a tiny difference, like that 0.01 difference, let's say on a 7-point scale, that would disprove the null hypothesis. It says equal. It doesn't say close to. It says equal. There's an equal sign in there, right? That population difference, that population mean difference equals 0. It's not close to 0. 5.01 minus 5.02 is 0.01. That is not equal to 0. We do not have access to population values because we are not God. So the p-value is another attempt, just like the confidence intervals were, to use our sample data to make a guess. We call these guesses inferences about our population data. We call this inferential statistics because we are using sample data to make inferences about populations. The p-value is the most common method that we use in science to disprove the null hypothesis. So modern science has taken this statistic and said, this equals, we're going to use this to try to disprove the null hypothesis about populations. Modern science is trying to disprove the null hypothesis. We do nothing statistically with our actual alternative hypotheses, the ones that you're trying to test, the one that you care about, the one that, you think might be true. We're not testing that at all. The null hypothesis is the idea that allows us to calculate p-value, though. It's the null hypothesis, which is the idea that allows us to calculate the p-value. So they're related, right? I was saying we use the p-value to try to disprove the null hypothesis, but without the null, you couldn't even come close to calculating the p-value because the p-value and the null hypothesis are completely intertwined. They are linked forever. Now, before I talk about how you disprove the null, we have to understand a basic concept. It's called the random sampling distribution. What is a random sampling distribution? Here's an example. A murder of crows is a group of crows, right? A distribution of data is a group of data. A random sampling distribution is a special distribution of data. It's a distribution of any statistic repeatedly sampled from any population, real or imagined. Okay, so a random sampling distribution is just a distribution of any statistic repeatedly sampled from any population, real or imagined. Population data, just like in that Monte Carlo experiment we talked about, can be imagined. This is a case that I'm not going to talk about the imagined of it. Nope. But I want you to see that there are infinite possibilities for random sampling distributions. You can have a random sampling distribution of standard deviations, of mean differences, of Cohen's d, right? There's an infinite number of possibilities. So let's make it less infinite. You had to see this one coming. The most important signal in a simple experiment is the mean difference, control minus experimental group, right? Most important statistics. So guess what? A random sampling distribution of mean differences is a distribution of mean differences sampled from a population, real or imagined, numerous times. Now, there are less possibilities here because it's mean differences, but there's still a lot of possibilities. Maybe, yes, that's all I have there for you. So the random sampling distribution of mean differences that we care about is the random sampling distribution of mean differences when the null hypothesis is true and the true population mean difference is 0. This is an imaginary distribution. It's not based on real data. It's made up, just like in the previous Monte Carlo study where we made up the population data. Well, in this case, we can make up a whole sample of random sampling data, okay? It's an imaginary distribution of mean differences repeatedly sampled from a population where the null hypothesis is true and the population mean difference is 0. And it's very specific. The other ones, they had many options. This specific distribution has a shape. It has a specific mean, 0. It has a standard deviation, which we call standard error. But it's a hypothetical distribution created from math theory, not created from our data. It's data independent, and it's always the same conceptually whenever you're comparing two means. In generic form, I call them the control and experimental group, but whenever you're comparing two means, you can insert the same logic for this whole unit. But ultimately, we're going to define all these different attributes in the next few slides, and then you're going to know where this random sampling distribution of mean differences is, where it came from, what it looks like, how we use it, why it makes sense. All this is going to make sense. But the one thing I want to point out, when you run an experiment, you select one mean difference. This is a distribution of all possible mean differences that you could sample if the null were true and there was no population mean difference. If you want to think about it, you can probably start connecting the dots right now. So there's a very important theorem, and this theorem suggests that the random sampling distribution of any statistic, including the mean difference, will be normally distributed as long as the number of observations in your sample is greater than 30. Now let's see this in action. So I just said what happens with the distribution with the central limit theorem. And I want to show you this in terms of a demonstration. Now, I'm not going to show you the demonstration with mean differences. I'm just going to show you it with a population, really weird population right here, right? So we have a population, but remember, we're looking for the random sampling distribution of mean differences. And essentially what you can do to create that distribution is do this twice and subtract the two distributions from each other. But let me show you what I mean. So let's sample one observation from this distribution of sample size 25, which is a little bit below our required sample size of 30 for the central limit theorem to work really well, but this is just an animation online. So what we're going to do is we're going to randomly sample 25 observations from this population. So you're going to see it's going to take a while to get all 25. We're going to calculate the mean. Now, if we were doing this for the mean difference, we would do it again, and we'd find another mean. We'd subtract those two from each other, and we'd keep doing that and doing that. But it's going to lead to the same result. So that's just one component of a random sampling distribution of a mean in this case. We could do the same thing for a mean difference, but don't get too confused, okay? So let's just do it. Let's just do it 5 more times, 5 more times, 5 more times, 5 more times, 5 more times. It's not showing you the animation here. I will do it one more animated time. This is a sample from a population, and then once it's all sampled, they calculate the statistic, which was a mean. It dropped below. You saw it drop below. Now let's do it 10,000 times. That weird distribution, when we sampled from it, randomly sampled from it, we found a distribution that looked like this. Now, if we are assuming that the null hypothesis is true, right, we're going to assume that the two populations have perfectly identical means. So we would just do it. Keep this in mind. We're going to clear this out. And now we're just going to do it again. We get the same distribution, right? So the distribution of the mean differences would be those two distributions essentially subtracted from each other, which means that the mean difference of that mean of 17 that you see here would just shift over to 0. But this holds true for the random sampling distribution of mean differences as well. It just requires an extra step and an animation that I haven't been able to find, and I don't want to create. So, but essentially you can see this. It doesn't matter what the population data looks like. The random sampling distribution of any statistic, mean, standard deviation, whatever, will approach normal. Let's do it again. I created a new distribution, another weird distribution. Oh, I didn't clear the lower, my bad. Go ahead, run that. We get another normal distribution when I did that 100,000 times. Let's clear it again. Let's make another fun distribution. I'm trying to get those all to be 0. All right. So mostly I'm trying to be a little too meticulous here. I'm just going to say, okay, this is our distribution. We have two basically strong polar answers. Let's do this 100,000 times. We get another normally distributed distribution of the statistic. If you do this twice, right? If you just did it twice, I won't clear the bottom. I'm going to animate another 100,000, you just see that two distributions were put on top of each other. So essentially the mean difference would become, all we're doing is taking each score minus itself. So the mean difference would become 0 essentially. Don't worry about that too much. But what I want you to see is that it doesn't matter what the parent population distribution looks like. That random sampling distribution of the statistic from that distribution will always be normal. Here, I'll do another fun one. It's gonna make it. It's the Rocky Mountains, you know. It's on your trip, on 70. Let's do it. Let's clear the lower. Let's do another 100,000. You can see that the random sampling distribution of any statistic is going to approximate a normal curve. And you can see that with your own eyes. You can play around with this yourself. So, very simply, the shape of the random sampling distribution of mean differences is normal-ish, normal-esque. In practice, we do use variations on the normal curve when we're doing our statistics, but for right now, for today's lesson, it's shaped like a normal curve. The random sampling distribution of mean differences is essentially shaped like a normal curve. Here's my reminder. What is this a distribution of? It's not just a normal curve. When people draw curves, they see it as one shape. No, this is a distribution of mean differences. So I put a bunch of little blue circles here to represent an infinite number of mean differences. Clearly, there's an infinite number of mean differences there. It's not, but it is. Okay, just trust me. The mean differences are the building blocks of the distribution. Yes, we can draw a curve around it and it's normal shaped, but then people forget this is a distribution of mean differences. So it's a distribution of mean differences when the null hypothesis is true and that distribution has a normal shape. We gotta remember that the normal curve and the normal S curves are mathematical ideas. So this distribution has limits of negative infinity and positive infinity. It goes to infinity and beyond and forever, and it goes out there forever. In this case, the units of this number distribution are just mean differences. Mean difference equals negative infinity. Mean difference is positive infinity. So our random sampling distribution of the mean differences when the null is true is shaped like a normal curve, normal-ish curve. It's made up of mean differences. It has a limit of negative infinity on the left and positive infinity on the right. Now, remember, this is the random sampling distribution of mean differences when the null hypothesis is true. When the null hypothesis is true, what is the most common, most probable average, median, mean difference, however you want to say it? It's always what number. In here, I'll say it. What is the mean difference when the null hypothesis is true? What do you think the average of all these mean differences is going to be? The most probable mean difference if the null hypothesis is true. The most average mean difference if the null hypothesis is true. The median mean difference if the null hypothesis is true. I didn't mention this when I talked about median and mean, but the median and the mean are identical in a normal distribution. So is the mode. That number is, say it with me on 3, 1, 2, 3, 0. 0. So when the random sampling distribution of mean differences is set so that the null hypothesis is true, this distribution has a mean, median, and mode of 0. The peak is 0. And you can see that on this picture. Now, this distribution has a standard deviation, and it's called standard error. When we do get to our calculations in the next unit, you'll have numbers to put on these graphs. But essentially, your standard error is the standard deviation of the hypothetical random sampling distribution of mean differences that assumes the null is true, or when the null is true. So all it is, standard error, is the standard deviations in this made-up fake distribution that represents the null hypothesis being true, that represents all possible mean differences that you can sample from negative infinity to positive infinity when the null hypothesis is true. It has a standard deviation. It's called standard error. Slight little sidebar here, but when standard deviation, even standard deviations of the random sampling distribution of mean differences, when the null is true, that we call standard errors, increase, the distribution gets flatter and flatter and flatter. The smaller your standard deviation, the more peaked your distribution is. So here we have a standard deviation of 1. That's the green one. It's peaked. You have a standard deviation of 2. That's the purple one. It's flatter. Standard deviation of 3. That's even flatter yet. Okay? So let's review what we have here, because we have now constructed the random sampling distribution of mean differences when the null is true. It's set so that the null is true. The shape is a normal distribution because of central limit theorem. Its building blocks equal the mean differences, right? Those are mean differences. It's not just a curve. Inside that curve is a bunch of mean differences built up on top of each other. The limits are positive and negative infinity. The peak, mean, median, mode of this distribution is the mean difference for when the null is true, and that is always 0. The standard deviation of this distribution is what we call standard error. The larger the standard error, standard deviation, the flatter and flatter the distribution becomes. But I will not make you draw this to scale. Nobody draws this to scale. We all draw the standard deviation picture that you see in front of us. The units are mean difference, but you can convert mean differences to Cohen's d's or maybe some other statistic. We will eventually convert these to something called a t-score, but don't even think about that. This is our null hypothesis in its most complete form. And it's actually very useful. All right, so I'm telling you this is a ruler. This is a probability ruler. Your random sampling distribution of mean differences is a probability ruler. Well, let's use it like one, okay? First things first, I got some questions. Is it mathematically possible to sample a mean difference of 100 if the null were true? Yeah, that's possible. This ruler goes from negative infinity to positive infinity. Is it likely? Well, I'd need more information, but right now, what in psychology is that likely? Probably not very likely. It's a pretty extreme mean difference. That's why I kind of chose it. Now, well, let's see. Does this ruler break? Is it mathematically possible to sample a mean difference of negative infinity if the null were true? Mathematically possible. Theoretically possible? Yes, it is, based on the math theory that we're using, based on the curve that we're using. Is it likely? Well, that's more debatable. If you're in the real world, no. We would never be able to sample a mean difference of negative infinity, so practically it's impossible, but mathematically it's possible. Is it mathematically possible to sample a mean difference of 1 if the null were true? Yeah, it totally is. Is it likely? Well, yeah, I think it is based on our past discussions. But right now, don't worry about if it is or if it isn't. I want you to see that you can use this as a ruler. This is a ruler that tells you the probability of sampling any mean difference if the null were true. And guess what? You ran one experiment. You ran one mean difference. And you're going to find a p-value of this mean difference. And I wonder if p-value stands for probability of sampling a mean difference has extreme or more extreme than the mean difference I sampled if the null were true. Okay, so our random sampling distribution of mean difference when the null is true is nothing more than a probability ruler. And I'm going to say this again. When you're hearing the word probability ruler and you're hearing the word probability, and you're hearing the word p-value, start to link those together. P-value is a probability. And where does it come from? It comes from your sampled mean difference. What's the probability of sampling a mean difference as extreme as the mean difference you sampled in your experiment if the null were true? We can figure that out now that we've constructed a probability ruler that tells us the probability of sampling any mean difference from negative infinity to positive infinity. We're going to use this blue ghost looking object that I've created to figure out the p-value. This is where our p-values come from. The probability of sampling a mean difference has extreme or more extreme than the mean difference I sampled, you sampled, we sampled if the null were true. So with p-value, in terms of the definition, I'm a bit of a stickler. There's a definition that everybody knows, but it's kind of imprecise. Some would say incorrect. I would say oversimplified and a bit misleading. The probability that your results are due to chance. That is not what our p-value is. What's the actual definition? It's the probability of sampling a mean difference has extreme or more extreme than the mean difference you sampled, I sampled, we sampled if the null were true. And when I'm thinking back to that funky little blue shape, that blue ghost looking curve that we created, I'm starting with all those little building blocks inside of it. I'm starting to realize that this is a third grade fractions problem. Calculating, mark my word, calculating p-value is a third grade fractions problem. Okay, here's the problem. I sampled a mean difference of 0.5. What's the probability of sampling a mean difference of 0.5 or greater if the null hypothesis were true? Remember I said probability of sampling a mean difference has extreme or more extreme than the mean difference I sampled if the null were true? Well, for this first example, I'm just going to say greater than, okay? That's just how I'm going to define has extreme and more extreme. It'll make sense in a few seconds. So I'm saying this is a third grade fractions problem. What do you think you're going to do, right? You got your ruler. You're probably going to find that mean difference of 0.5. And you're going to figure out the probability of sampling a mean difference of 0.5 or greater on this funky little blue normal shaped curve that's set to so that the null is true. And here, that's exactly what I did. I found my mean difference of 0.5. I put it on my ruler, and I said, okay, I colored some of my blue circles, I colored them red and blue. What is the probability of sampling a mean difference of 0.5 or greater if the null hypothesis were true? It's all those red circles, I guess they're ovals, divided by all the blue circles, including the ones that have blue and red in them, right? That's why they're not one color, they're two, because those circles are both part of the whole. The bottom is the whole distribution, and the red is the part of the distribution where the mean difference has extreme or more extreme than the mean difference I sampled of 0.5. That's it. This is a fractions problem. Red over blue. This is your p-value. This is the concept of your p-value. It's not anything special. Oh, my p-value is that red area divided by the whole or the blue area, right? It's a probability of sampling a mean difference has extreme or more extreme than the mean difference I sampled if the null hypothesis were true. That's what it is specifically. That's what it is conceptually to me. I don't understand the chance. What's your chance function? If you don't get that, just ignore that. But ultimately, this is a fractions problem from it's a complicated fractions problem from third grade. I think they teach you all earlier. Maybe it's second grade now. I do not know. I am too old. Okay, but are you with me? Do you see it? Right? If you don't see it, we're going to talk about this in class. So let's just do the problem again with a different interpretation. What is the probability of sampling a mean difference has extreme or more extreme than the mean difference of 0.5 if the null hypothesis were true? So we can interpret has extreme or more extreme in a different way. So we can interpret it to mean 0.5 or greater, just like we did before. However, we can also interpret it to mean the mirror image of 0.5 and greater. So if we think about the negative side of this curve in terms of absolute values, right? 0.5 and negative 0.5 have the same deviation from the 0 point. So they're both equally extreme. And if you go to the tails, those are more extreme than the mean difference we sampled. So essentially what's going on here is we just reinterpreted has extreme or more extreme to include the mirror difference to mirror image to include the absolute value. Like we're saying the absolute value of a 0.5 mean difference is equal to the absolute value of a negative 0.5 mean difference. And then it just all kind of works its way out. This version where you look greater than or in the direction of your hypothesis, remember I said I always set up my mean differences so that positive numbers are in line with my hypothesis. This is what we call a one-tailed test. This is what we call a two-tailed test when we account for its negative mirror image. And frankly, from this point forward, you know what the difference between a one-tailed and a two-tailed test. But here's the reality of it. In modern psychology, in modern neuroscience, no one is going to let you publish a one-tailed test. We just don't trust you enough to believe that you predicted, the direction that you found. We just don't trust it. So you always have to use a two-tailed test because we as scientists don't trust other scientists to tell us the truth. And that's really the reason why we use two-tailed tests. But ultimately, it's still a fractions problem, red over blue. It's just the red area just got twice as large. That's all that happens in a two-tailed test. In a two-tailed test, your p-value is doubled. So in a one-tailed test compared to a two-tailed test, your p-value is cut in half. Same idea, same math, same. It still works here. I don't know how you learned fractions, but when I was a kid, the Ninja Turtles were huge. So all my teachers made all our fraction problems pizza problems, and they used the Ninja Turtles as characters. So let's just live through that tradition of our youth one final time so that we're not scared of what a p-value is. Leonardo from the Teenage Mutant Ninja Turtles created a bell-shaped pizza that we've spent the last, I don't know how many slides designing, right? We've designed its shape and all that. Leonardo cuts one slice defined by a mean difference of 0.5. What proportion of the pizza is Leonardo eating? If we want to understand probability and proportion, they're the same thing. If you multiply probability by 100 or proportion by 100, then you get percentage. Well, Leonardo's eating about 40%. Michelangelo comes in, and he thought it was a two-tailed test, so he ate 80% of it. Right? That's really, I really want you to see that this is nothing special. This is just a fractions problem. I'm teaching it to us at this lower level so that we understand the concepts. But I just want you to understand that while it seems scary, ooh, p-value, I'm terrified, where's it come from? All this horrible stuff. Like, at the end of the day, conceptually, what we're doing is nothing. Well, okay, it's a little different than what we did in third grade. Maybe it's earlier for you all now. Maybe it's second grade. But ultimately, it's just a pizza's fraction problem. That's it. Don't be scared of it. So cowabunga, right? Like, take some comfort in the fact that you understand a p-value because you were asked to do these fraction problems in elementary school with pizzas. The only thing that's different is the shape. That's the complicated thing, the shape and how you draw the slices. The shape is not a perfect circle. It's, this weird bell-shaped curve, and the slices aren't 8 slices, 10 slices, whatever. They're defined by the mean difference of your sampled mean. But other than that, it's simply a fractions problem. Your p-value, if you look at it, if you want to be the most precise, it's the probability of sampling a mean difference. Has extreme or more extreme than the mean difference you sampled if the null were true. And 99% of the time in psychology and neuroscience, that means a two-tailed test. The only time I've ever gotten away with one-tailed tests was when I ran replication studies and my p-value was close to meeting the value of significance, but I was also forced to only make a directional prediction, so I was predicting the same effect again, and literally I couldn't publish the paper if I found the opposite effect, right? If I found a significant difference in the opposite direction from what I predicted in my replication, my study's over. So ultimately, like, one-tailed tests, in my opinion, can only be used, well, It can only be used with a very strong prediction, very strong pre-existing directional prediction in line with your hypothesis in general. Now, most of the time for me, I really wish I could use a one-tailed test because I do make very strong one-directional predictions. But also that means if I don't find what I was predicting, but I like the information I found, I'm not technically allowed to use that information in any future studies. So ultimately, in psychology, in science, we are going to be forced to use two-tailed tests most of the time. You might be able to get away with it. I've gotten away with it a couple times in my published work, but it was after I made strong predictions. But I want to teach you a life lesson. To be a good statistician, you need to connect the new to the old. You understand the basic math. You probably don't get the normal curve. You don't understand that, but you definitely understand the conceptual idea here. This is a fractions problem. Don't be scared of it, right? Connect your old knowledge to fractions with your new knowledge about the normal curve. And this will help you conquer your fear. Part of what I'm doing today is being a social psychologist and letting you make fun of how unscary this is. Like, I'm putting a goofy second grade Ninja Turtles image on the screen because this is a goofy problem. Don't be worried about it. Also, I want to tell you other reasons why you shouldn't be worried. We're going to heavily rely on computers to check our calculations because human error is bad for statistics, is bad for research. So ultimately, right, like, don't be so scared. Like the hand calculation stuff, if you mess one of those up, I'll probably look the other way, right? It's checking it with your computer that's going to be the most important thing. Don't trust hand calculations in general, but don't be worried about them. But also, if we know what we're doing, this stuff is not scary at all. In fact, all p-values that you've ever seen have been some version of this fun little fractions problem. So I really just want you to move forward and not be scared. There's nothing to be scared of here. Now we have to connect our p-value to disproof. How do we know if we've disproven the null hypothesis? Now, scientists agree not based on any math or any theorem. We just consensually agree on this across fields due to many historical factors that if your p-value is less than a probability of 0.05, if you multiply that by 100, a probability that's also less than a 5% likelihood, or a 0.05 proportion of the pizza, I'm still going to make fun of this problem, that equals disproof. So, small is significant. Not small is not significant. Small is significant. Not small is significant. 0.05 out of 1 is small. 5% out of 100% is small. Anything less than 5% is small. Small is significant, and what that means is we are taking this as evidence that we have statistically disproven the null hypothesis. I am saying disproven. You'll hear a lot of people say reject because disproof has different meanings to other people. But for right now, realize science works through disproof. This is the math that we use to try to disprove theories and ideas in science. And the cutoff level, technically we would call that alpha, that 5% cutoff level, that probability of 0.05, that proportion of the pizza of 0.05. Notice probability and proportion are the same. That was determined by consensus. And a logic, I'm not saying that we're not thinking about it. People think about this question quite intensely. But ultimately, this is what we do. We try to disprove the null with our statistics. We say reject a lot of the times. I'm okay if you say disprove to me. Probably don't write that in your papers. But we're trying to disprove the null hypothesis that the two means are perfectly identical. If the probability of sampling a mean difference has extreme or more extreme than the mean difference we sampled, if the null were true, is less than 5%, is less than a probability of 0.05. Those are the same thing. It's less than proportion of the pizza of 0.05. Same thing as well. We say we have disproven the null hypothesis. Now, there's a 5% chance that we're wrong and we're making an incorrect rejection, but you need to realize that this is what we do. Science is about disproof, and we're trying to disprove the null hypothesis. This may not set with you well, and I'm okay with that. We can talk about that in class, but I just want you to know what we're doing, and now you know. So technically, your p-value has to be less than 0.05 to be quote-unquote statistically significant. So when your p-value is 0.04999999 all the way out, right? Technically, your null has been statistically disproven. Some folks are uncomfortable with the word disproven. I get that. But I'm going to keep saying disproof because my job is to help bridge the gap between the way you think and the way we do science. So I'm kind of using some psychology to teach this course, right? This isn't how I would teach math majors at all. But for you all, I want you to see like, okay, we're really trying to disprove the hypothesis that the two means are perfectly identical. A lot of folks use this and say rejected. Now, if the null were true and the population means were equal, 4.9% of the time, I would sample a mean difference this extreme if my p-value is 0.049. 4.9 out of 100 experiments would say we found a difference when one didn't exist. You're only eating 0.049 proportion of the pizza, and that's basically not eating at all, right? 4.9% of a pizza, proportion and percentage are related, is like 1/4 of a slice. I'm not going to count that against my caloric. I'm not going to feel bad about that, eating that one little sliver of cheesy happiness. But there's a 4.9% chance that we're wrong and the null is true. This is like a false hit. I call it a false hit because we're trying to, we want to, as scientists, reject the null hypothesis. You'll see why in a second. This is also known as a type 1 error. A type 2 error is when you say that it's not significant when the true population means are actually different. And like I said before, this is not based on this value of 0.0499999 or 4.99999%. It's not a mathematical decision. It's more of one of consensus that everyone and not everyone, a majority of people in a majority of scientific disciplines agree upon. The only scientific discipline that doesn't really use p-value to my knowledge is physics. Physics uses a Cohen's d of 6 as their level of finding a discovery, which is really cool. I hope one day we get control over measuring human behavior so well that I can use the 6 sigma or that sort of criteria for quote-unquote a discovery. I just worry that that would be too conservative and we wouldn't be able to find much. We'd only be able to find the strongest predictors of human behavior. But who knows what 100 years may bring. Now, when your p-value is greater than 0.05 and you only have p-value, I've already shown you confidence intervals. I'm assuming you do not know anything about confidence intervals. What do you know? Well, you know that you have not disproven the null. Have you proven it? You know nothing. You have not disproven the null, but you also have not proven the null. You know nothing. Statistically, you have not disproven the null. Statistically, you have not proven it. You know nothing, Jon Snow. You know nothing. When your p-value is greater than 0.05, you know nothing. When your p-value is greater than 0.05, you know nothing. You do not know that the two means are the same. The only way you can get at that is with the confidence interval method I showed you in last lecture. But technically, you know nothing. P-value is greater than 0.05. You have not disproven the null. You have not proven it. Statistically, you have not disproven the null. Statistically, you have not proven it. You know nothing. Jon Snow, you know nothing. P-value is greater than 0.05. Jon Snow says, I know nothing unless I calculate the confidence intervals of mean difference, and then maybe I can get at that. Are my two means essentially practically the same, like we did in the last lecture? When p is less than 0.05, you have small. That's a small value. Small is significant. Not small is not significant. Small is significant. Not small is significant. You know that the null has been disproven statistically. It's been rejected, but I'm going to say disproven. If you like the disproof, if you're like me and like a little bit of hyperbole, exaggeration in your discussion, then join with me. Yeah, statistically, your null's been disproven by the agreed upon standard of scientists that there's some error in, and we get that. As long as you get that, like, you could be wrong in your conclusion, then we're cool. But essentially, yeah, we've disproven it with the caveat that we know we could be wrong. Like, there's a 4.9% chance that really the null's true, but there's always a chance that the null's true, even when I sample a mean difference as extreme as infinity. P is less than 0.05, your null has been disproven. Small is significant. P less than 0.05, hey, that's small, right? The largest p value you can get is 1. You cannot get negative p values, right? So that's small. Small is significant. What significant means? Significant doesn't mean the effect is important. We talked about that in the confidence interval lecture. It doesn't mean the effect's important at all. I still want to see that Cohen's d. You can have a significant p-value in a tiny effect. But what do I know? The null has been disproven. P less than 0.05 is small. Small is significant. The null has been disproven. P is less than 0.05. Small is significant. We have disproven the null that the two means are perfectly identical. P is less than 0.05. The null has been disproven. We know that the two means are not perfectly identical. Well, we don't know that. There's a 5% chance we can be wrong, but every scientist treats it this way, treats it like we've disproven the null. It's the only method we got for disproof, and we can't prove things in science. We learned that the hard way by listening to Freud for way too many years. Now, what do you do when P is perfectly equal to 0.05? People will disagree with you on this. Here's the thing. It's just a rare event. So let's not worry about it too much, okay? In my class, it's a rare event. I will really not have you think about P equals 0.05. What I'm going to do is I'm going to tell you this. Round it out. Round your p-value out to as many decimal places as possible. It rarely is exactly 0.05. 0.051, you know nothing. 0.0499999, that equals disproof. I know that seems like unfair or whatever, but that's how it is. That's how we do it, right? If your p perfectly equals 0.05, okay, if that situation comes up, I mess up on a problem set, you're going to write up your manuscript. I am perfectly fine with you taking the win. Just take the win, but improve your methods on round 2 of your study. Like if you find this in your research methods project, take the win. I do not mind. But, yeah. Take the win. When your p is greater than 0.05, you literally know nothing. Your two means are not equal. You have not proven the null hypothesis. You also don't have enough evidence to statistically disprove or reject the null hypothesis. But your confidence intervals of the mean difference of the Cohen's d actually give you an advantage. With them, you can tell p when your confidence interval includes what value. You know your p is greater than 0.05. I'm not going to tell you, but reason it out. Think about what the Cohen's d is when the null hypothesis is true and your two means are perfectly identical. It's not really hard because your mean difference is and your Cohen's d would be right? Exactly. When we convert our confidence intervals of the mean difference to our Cohen's d limits, then we can start to interpret it. For example, I have an example right here. Two mean differences, negative 0.1 to positive 0.1. Average standard deviation is 2. My 95% confidence interval of the Cohen's d is negative 0.05 to positive 0.05. Remember, our small value is 0.2. Medium is 0.58. 0.8 is large, right? So here, these are 4 times less than small. Anything that's 4 times less than small is tiny, non-existent, nothing's there. I'm going to do the same thing I did in the previous lecture, and I'm going to argue with this. If I have this specific confidence interval of the Cohen's d, that I have found that the two means are essentially practically the same. I have strongly supported, I wouldn't say proved, I wouldn't go that far, but strongly supported the null hypothesis. Confidence intervals are better, and they give you basically the same information as p-value. And once you get it out of your mind that a smaller and smaller p-value doesn't really mean anything, look at that example from Jeff Cummings' work. Like, what's it mean? It doesn't mean anything, except the one thing it means is you had enough precision to find significance. Maybe, right? Maybe. But everything in stats, everything in science boils down to the first day. Reduce your standard deviations. Reduce the errors in your studies. When you do that, you reduce your confidence intervals. You make them tighter. You increase your precision. And by increasing your precision, you reduce your p-values. If p-values could show you precision beyond a magical number that's less than 0.05, and if I've never thought about them in terms of indices of precision, but if we had some standard interpretation, I'd be more okay with them. But right now, like, we just don't have that precision. It just tells you how far away your mean difference is from the hypothesized mean difference when the null is true. It doesn't really work that way, right? We need to know the limits of that mean difference, the lower limit, the upper limit, not just the middle. We need to know the entire confidence interval. We need to think about it. What would my p-value be with the worst case scenario? What would my p-value be with the best case scenario? So ultimately, we're at the end of this unit, and what I'm trying to do is I'm trying to connect you with very personal examples, very simple. Like, I'm trying to simplify it so that we can get it, we can connect to it. That's what this whole section was about. I want you to see that good science is control. You've learned that at a young age. What's the mathematical statistic of control? Well, per condition, it's your standard deviation, right? Per the entire experiment, the best estimate of control, of precision of our estimate, are those confidence intervals. And don't forget what I showed you in the last lecture. Less than 50% of the time in that simulated Monte Carlo study done by Jeff Cummings did your p-value lead to truth. That doesn't mean give up on your p-value, right? I went through a next step. Our confidence intervals did lead to truth in that study, but they were quite imprecise. You are entering a scientific field, and it's not just psychology, it's not just neuroscience, it's medicine, it's other fields as well, where we have not spent enough time focusing on reducing error in our measurement, increasing our precision of our estimates of the population values. So I hope this makes sense. Please bring your questions tomorrow, but your conceptual test has been posted since the first day of class, and I'd like you to start answering those questions. They're essay questions. You can work with a friend. You just have to cite it. I don't mind that. I do mind if you all actually share written answers. You can talk about it all day, but once you start sharing text, you've crossed my line of cheating because I've made it very clear. As a social psychologist, what do I know? We work better as a group. We have a lot of power as a social unit, so I want to utilize that power. But at the same time, if you socially loaf and don't do your work, you're not going to get the gains that you're paying a lot of money for. Feel free to use me, text me, ask me questions. I'm here for you. But I hope it's starting to make sense, and I hope you're starting to connect to it personally. This is our last homework problem before the test. Just tell me if they're significant, not significant, or impossible. And you have a bunch of p-values there. 1, 2, 3, 4, 5, and 6. You sampled, this is just setup. You've sampled a mean difference of 4. Graphically create the null hypothesis with every component. This was most of today's lecture. Add your sample mean difference to the graph. and show me the p-value in a color fraction. I'm not asking for a number. I'm asking for a color fraction. I'm asking for a visual. I'm asking for a graphic. Number 3, redo number 2, ideally directly below where both graphs share the same number line, or directly above, or whatever. But now you have a vastly larger standard error. And I want you to sort of go back. I only talked about it in one slide. Standard errors is, what is that in this distribution, right? Oh no, I talked about it. Show me what happens to the random sampling distribution of the mean difference when you have a vastly larger standard error. Number 4 is saying do the same thing, except you have a vastly smaller standard deviation of the random sampling distribution of the mean difference. What you should understand there is that, oh, is that a typo? No, it's not. I'm using synonyms now for that distribution, and this should start to make sense. And then look at those 3 graphs and tell me how your standard error will impact your p-value. Will larger standard error increase your p-value? Will it decrease your p-value? Go back to, you can probably logic that out based on my discussion of precision, okay? So what should you expect? I'll just state it this way. If smaller standard deviations are better science, and standard error is standard deviation in this graph, what are you expecting? Define p-value correctly. Just look at your graph, define it. Define the null hypothesis in words and symbols. Particularly make sure to focus on the signal we care about. I showed it 2 different ways, right? But what are we doing here? We're calculating an experiment. We cannot separate the control and the experimental conditions. So we're really focused on mean differences there, right? That's the signal. So give me the version in mean differences. Sometimes I want to make you work for it, and right now I just gave it to you. So making sure you're reading, you're paying attention. True or false, we prove things in science with the p-value. Even without the p-value, I guess, do we prove things in science?